The rectangular coordinate system is the first coordinate system we become familiar with. The rectangular system consists of three perpendicular axes. The x-axis, which defines length, the y-axis, which defines y, and the z-axis, which defines height. These three axes are pairwise perpendicular to one another. To represent a point in this system, we must specify a length, a width, and a height for that point. Suppose, for example, point P0 has an x-coordinate of x0, which we mark off along the x-axis. It also has a y-coordinate of y0. To reach the point, we can move from the end of x0 and mark off y0 along the y-axis. Then, from the end of that displacement, we can draw the height z0 to arrive at point P0 with coordinates x0, y0, and z0. As can be seen, the range of x-axis extends from negative infinity to positive infinity, meaning this coordinate can take on any value from negative infinity to positive infinity along this axis. The same holds for y and likewise for z. Therefore, by allowing x, y, and z to each range between negative infinity and positive infinity, the entire space is covered by this coordinate system. X can be either positive or negative, likewise for y, likewise for z. Thus, each of the three coordinates has two possible signs, giving a total of 8 regions in space. That is 2 times 2 times 2. So, this coordinate system divides space into 8 regions. Let us now examine these regions one by one. In region 1, all three variables are positive. In region 2, x is negative, y is positive, and z is positive. In region 3, x and y are negative and z is positive. In region 4, x is positive, y is negative, and z is positive. In all four of these upper regions, z remain positive, while only the sign of x and y change. Now, if we consider the same for sign combinations with z negative, 4 additional regions result. Region 5, region 6, region 7 has x and y negative and z negative as well. And finally, region 8 has x positive, y negative, and z negative. Now, let us turn to defining the unit vectors of this system. A unit vector requires two essential properties. First, it must have unit magnitude, and second, its direction must coincide with the direction of the corresponding principal axis. Along the x-axis, we mark off one unit having unit magnitude, and we assign its direction to be positive x in the direction of the principal axis, that is in the direction of increasing x. This is defined here as a hat sub x. We mark off one unit along the y-axis in the direction of increasing y, and we assign its direction to define a hat sub y. We mark off one unit along the z-axis in the direction of increasing z, and a hat sub z is likewise defined. As you can see, these vectors are pairwise perpendicular. We now wish to define a vector in this coordinate system. A component along the x direction, a component along the y direction, and a component along the z direction are summed together to define a vector in this system. The component along each direction may be a function. It need not necessarily be a number. It can be any function of any variable such as x, y, or z themselves, or it may even be a function of variables belonging to another coordinate system. Now, suppose that we want to draw a vector in this system, and for simplicity, let us assume that a sub x, a sub y, and a sub z are numbers. We proceed by marking of a length equal to a sub x along the x-axis in the direction of a hat sub x, that is, we mark off a sub x on the x-axis and its direction of a hat sub x. Then from the end of that segment we move a distance a sub y in the direction of a hat sub y. Here these are assumed positive for ease of illustration. The sum of these two vectors, according to the triangle rule of vector addition, is obtained by connecting the starting point to the end point. Thus, a vector shown here in yellow represents the sum of these two vectors. Now, from the end point of this vector, meaning from the tip of the yellow vector arrow, we must draw a sub z, whether positive or negative. Here we have assumed it to be positive. We then connect the origin to this final point to form vector A, shown here in white. The magnitude of this vector, the magnitude of A, can be obtained using the Pythagorean relation, since a right triangle is formed here. So we can obtain the magnitude of A from this relation. Now, substituting this in, the magnitude of vector A can be obtained from this relation. To obtain the unit vector corresponding to vector A, we must divide vector A by its magnitude. Example: consider A 2 times a hat sub x plus 3 times a hat sub y plus 4 times a hat sub z. We first draw this vector. 2 units in the positive x direction. We mark 2 times a hat sub x along the x-axis. From the end of this vector, we move 3 units in the y direction, i.e. 3 times a hat sub y forward. Or simply we can obtain 3 times a hat sub y like this, and also 4 times a hat sub z like this. Now, as discussed, move 3 times a hat y from the end of 2 times a hat sub x, then 4 times a hat sub z from the end of 3 a hat sub y. Now we connect the starting point to the end point, and vector A in the coordinate system is obtained. The magnitude of vector A can be obtained from this relation f's A equals to the square root of 29. Now, if we wish to find the unit vector along A, we must divide A itself by its magnitude, i.e. the square root of 29, which gives the corresponding unit vector. Another example. Consider the following problem. What is the angle that vector A makes with the xy plane? We first draw vector A, one unit along A hat sub x on the x-axis, then moving along the y direction, and then 3 units along A hat sub z moving along the z direction. This gives us vector A. The angle that vector A makes with the xy plane is denoted here by alpha, which in fact the angle it makes with the same yellow vector described previously. Now, if we consider this right triangle, the angle in question is alpha, and we can use this relation tangent alpha equals to a sub n divided by a sub t. Now we need the magnitude of a sub t, the magnitude of the yellow vector, which can be obtained from this equation, equals to a square root of 3. A sub n is the component along the z direction, which is 3. Therefore, tangent alpha equals to 3 divided by the square root of 3 equals the square root of 3, and alpha is obtained 1/3 of pi radians or 60 degrees. Addition and subtraction of vectors. Let vector A equal a sub x times a hat sub x plus a sub y times a hat sub y plus a z times a hat sub z, and let vector be defined as shown here. We wish to find the sum of these two vectors. If we group together the components along each common direction in vectors A and B, we see that the components sharing the same direction are added together, and the result is the sum vector. For vector subtraction, it likewise suffices to subtract the second vector from the first, that is, to subtract the component of the second vector along each direction from the corresponding component of the first vector along the same direction for x, and likewise for y and z, in order to obtain the result of the subtraction. Defining a vector by its initial and terminal points. It may occur that a vector in three-dimensional space within the rectangular coordinate system does not originate at the origin of coordinates. Suppose we have a vector connecting point P1 to point P2. Vector P1, P2. Point P1 has coordinates x1, y1, and z1. Point P2 has coordinates x2, y2, and z2. To obtain vector P1, P2, we first connect the origin to point P1, giving vector P1. We have vector P1 equal to x1 times a hat sub x plus y1 times a hat sub y plus z1 times a hat sub z. Now we connect the origin to point P2, giving vector P2 as well. x2 times a hat sub x plus y2 times a hat sub y plus z2 times a hat sub z. Now we have a vector sum. Vector P1 plus vector P1 P2 equals vector P2. From the triangle rule of vector addition, we can write this relation. From this, P1 P2 equals vector P2 minus vector P1. Here we use the result of vector subtraction discussed in the previous part. So vector P1 P2 becomes x2 minus x1 times a hat sub x plus y2 minus y1 times a hat sub y plus z2 minus z1 times a hat sub z.